and I'm also going to say which packets are really lost. So that means you're sending packet 1, then packet 2 and 3, then packet 4, 5, 6 and so on depending on the congestion control mechanism, and certain packets could be lost due to congestion. So let us say these are the packets that get lost. So if a packet get lost, you have timeout according to the congestion control mechanism and then retransmit that many bytes. So we are also going to assume that the packets are going to successfully make it to the destination after the first retransmission. Okay. So let us start with AIMD. So if you again remember how AIMD will work, you do an additive increase. So in the first window, it's also called the round trip time, as we saw from the earlier examples. You wait for one round trip time to get an acknowledgement, right? So in that one round trip time, how much you could send is the window size. So in the case of AIMD or all the three mechanisms, you start with one data packet for the window size. So that's one, so you send one packet, so that's sequence number 1, and these are the 4 packets that are lost. So packet 1 is not lost, so it makes it to the destination. So the next round trip time you are increasing it linearly, additive increase. So you are sending 2 packets instead of 1 packet. So you are sending packets 2 and 3. They both make it to the destination. Then in the next round trip time you are sending one more than the previous window, so you are sending 3 packets. So you are sending 4, 5 and 6 as the packets. These are the sequence numbers. Now I have given you that packet 5 is lost, so that means you have to drop to half the previous congestion window size. So previously in this window round trip time you sent 3 packets. Now you have to drop to half of this. So 3 divided by 2 is 1.5. So we do an integer arithmetic here. So we again start with 1 packet in the next round trip time. So again 5 is lost. So that means 4 is considered to have been received. So you retransmit packet number 5. Again, as I said, after the first retransmission, the packet makes it to the destination. That's how we assume in this problem. So in the next round trip time you increase the sending rate by 1. So instead of 1 packet now you send 2 packets, which are 6 and 7. So even though you have already sent 6, to keep things simple in our calculations, after a packet is lost we are going to retransmit everything from that point, if even the others are making it to the destination. So you are going to send 6 and 7. So both make it to the destination. So now you are sending one more than the previous window, so sending 3 packets, so 8, 9 and 10. Then you're sending one more than the previous window, 11, 12, 13, 14, 4 packets. Now all of them make it to the destination, so you're increasing the sending rate by 1, you're sending 5 packets. Now I have given you that packet number 15 is lost. So that means the next window you are going to reduce the sending rate by half of the previous window. So that is 5 divided by 2, 2.5. So we send 2 packets in the next round trip time. So that, and again now 15 makes it to the destination, and 16 also makes it to the destination. So in the next round trip time you are going to send one more than the previous window, so you're going to send 3 packets. Then you're going to increase by 1 more, so you're going to send 4 packets in the next round trip time. Now packet number 22 is going to get lost. So in the next window you slow down by half, so 4 divided by 2 is 2 packets, so you send 22 and 23. Now both make it to the destination. So the next window you increase by 1, so 3 packets make it to the destination, and again all the 3 make it, so that means we increase by 1 more, so 4 packets. Now packet 27 is dropped, so that means the next window you send 27 and 28, half the previous window size. Now in the next window you could send 3 packets, but you want to send only up to 30 packets, so that's why you send only 29 and 30. So what we are going to estimate based on this process is, with AIMD, if these are the 4 packets that get dropped, you're going to take 16 round trip times to send 30 packets. Now based on this information, and if you're given also the round trip time, you could estimate what is the throughput, means how much you could send per unit time. So it takes 16 round trip times for 30 packets. So what we are going to do is the throughput is 30 packets are sent in 16 round trip times. So 30 packets, each packet size. So packet size also needs to be given to you. So assume a packet size is 1 kilobyte of size. So 30 packets times 1 kilobyte, and you know from our first module of earlier modules, 1 kilobyte is 1024 bytes. So 30 times 1024 bytes divided by 16 round trip time, and each round trip time is say 100 milliseconds. So all these things are given to you. What is one round trip time, and what is the packet size, and what packets are lost. So you do the math and you figure out that you could convert things to bits. 1 byte is 8 bits, so you could send 15 3600, this much bits per second. So again, what you are given is, so if you read the earlier slide, you are given all this information. You are given that you want to send packets with sequence numbers 1 to 30, and these are the sequence numbers of the packets that are lost, and this is one round trip time value, and this is the packet size, 1 kilobyte of data. So you're given all this information and you have to work out the problem like this. So once you found the round trip times, the throughput is simply the number of packets you are sending, in this case 30 packets, divided by 16 round trip time, and convert the units accordingly. So each packet is 1 kilobyte, which is 1024 bytes. That means also 1024 times 8 bits. So that is the numerator, 30 times 1024 times 8 divided by 16 round trip time, and each round trip time is 100 milliseconds. So 16 times 100 milliseconds, and again 1 millisecond is 10 to the power negative 3 seconds. So do the math, the conversion of the units properly, and you should be able to find the throughput. Okay. So any question on this so far? Alright, so now let us do for the same scenario the slow start algorithm and see how many round trip times we encounter. That means same scenario means you want to send 30 packets, and these are the 4 packets, the same sequence numbers that get lost. So in slow start, what you do, you start with again 1 packet, and that packet makes it to the destination. So the next round trip time you send 2 packets, double the previous window size, so you send packets 2 and 3, both make it. So in the next round trip time you send twice the previous window size, so you send 4 packets, so you send 4, 5, 6, 7, but in this case packet 5 gets dropped. So in slow start, what you do, you note down 2 things. You set what is called the congestion threshold to be half the previous window size. So previously you had 4 packets, so the congestion threshold is half the 4, which is 2, and you slow down all the way to 1 packet and do an exponential increase until you hit the congestion threshold, and after you hit the congestion threshold you do an additive increase. So that's how you do slow start. So that means in the next round trip time you send only 1 packet, which is packet number 5, the packet that got lost. And the next round trip time you double that, which is 2 packets, and that is also a congestion threshold. So you have reached the congestion threshold. That means you have done the exponential increase until then. So after reach the congestion threshold of 2 packets, you should do only additive increase. So you increase the number of packets by 1. So in the next round trip time, you send 3 packets. All the 3 make it. So again, you do only additive increase. The next round trip time, you send 4 packets. All the 4 make it. Then the next round trip time, you send 5 packets. Now packet number 15 gets dropped. So that means you have to note down the congestion threshold as half this size, which is 5 divided by 2, which is 2. We'll do only integer division. So in the next round trip time, again this is slow start, so you again start all the way to from 1. So in the next round trip time you send only 1 packet, which is 15. That makes it successfully, so you double the congestion window size, so you send 2 packets, 16 and 17, and that's also a congestion threshold. So that means the next round trip time you do additive increase, which is 18, 19, 20, 3 packets. Then you increase by 1 more, so 4 packets. Now packet 22 gets dropped. So you set congestion threshold to be half of this, which is 2 packets. So you go all the way to 1, and then do a slow additive and then okay, this is congestion threshold is 2, so you can double it. So you send 2 packets, and now from now on you do additive increase. So in the next window you send 3 packets. So again 27 gets dropped, so the congestion threshold now is half of this 3 packets, which is 1. So that means in the slow start process, next you start with 1 packet, and from there itself, since you reach congestion threshold, you have to do only additive increase. So you increase by 1 packet, which is 28, 29, and you could actually send 3 packets in the next round trip time, but you want to send only up to 30 packets. So that's why you send the last 30th packet in this round trip time. So it takes up to 18 round trip times to send 30 packets with slow start. That's what we have figured out now. So now we have to calculate the throughput in the similar fashion. 30 packets, each packet is 1 kilobyte, divided by 18 round trip times, and each round trip time is 100 milliseconds. So substitute do the conversions for bytes to bits and milliseconds to seconds, and this is what you get as throughput. So you get, say, 136,000 something. So what we got with AIMD alone is 153,000 something, and that's essentially because it's larger, because you had a fewer round trip time, 16 round trip time, which is in the denominator. So you send 30 packets in 16 round trip times in AIMD, whereas you encounter 18 round trip times to send 30 packets with slow start. So as you can see, slow start is essentially a slow process compared to even AIMD. Now let us do the same scenario with fast recovery. So we start with 1 packet. So the way fast recovery does is you do exponential increase for the first time until you encounter a packet drops, and then reduce the congestion threshold and continue from the congestion threshold itself by doing additive increase. So that's what we are going to do. So start with 1 packet, double it up, 2, 3, double it up, so 4, 5, 6, 7. So 5 is getting dropped. So congestion threshold is now going to be half this congestion window size. So 4 divided by 2 is 2. So that means the next round trip time you right away continue from the congestion threshold instead of slowing down all the way to 1. So in the next window you can send the congestion threshold amount of packets, which is 2 packets, 5 and 6. And both make it. So the next window you do additive increase, so that means you can send 3 packets. Then the next window you can send 4 packets. Next you can send 5 packets. So again 15 gets lost. So that means the congestion threshold is now 5, the congestion window size, divided by 2. That means the next window you can send the congestion threshold amount of packets. So 15 and 16, there are 2 packets. Then you can do additive increase. So send 3 packets, then 4 packets. So again 22 is dropped, so you set the congestion threshold to be half of this 4, which is 2. So you send 22 and 23, and then do additive increase. So 3 packets, and then you can increase to 4 packets. Now again 27 gets dropped, so the congestion threshold is half of this window size, so which is 2 packets. So you can send 27, 28, and then you could send 1 more packet, because you can send 3 packets in this window, but you want to send only up to 30 packets, so you send only 2 packets. So that means you need only 15 round trip times to send 30 packets, which is the smallest of the 3. So accordingly we can estimate the throughput to be 30 packets. Each packet is 1 kilobyte per packet, and then divided by 15 round trip times, and 1 round trip time is 100 milliseconds. So do the math and you will get 163,840 bits per second, which is the largest throughput among the 3 algorithms. Okay, so let me stop here and save this video, and I have one more